I don't think that we need to present again, Oleg.
No, fine.
So please start.
Okay, I'm just trying to find my mouse. Yeah. Okay. So, do you see my screen?
Yes.
Okay, good. So just to summarize what we have done the last time. So we studied this Mathieu equation, which was actually a one-parameter family of equations. So we considered this parameter lambda as fixed, and one parameter family was parameterized by this energy E. And then to every equation in this family, we associated a value of monodromy parameter, so this quasi-momentum mu. And we asked two questions. So one was this direct monodromy problem, which was to find mu in terms of the energy, so monodromy in terms of the equation. And this was solved in terms of Hill determinant. Now, the inverse monodromy problem was to find the energy given monodromy. Okay, and this was perturbatively solved using this infinite fractions. And then we arrived to analogous question, but now in the context of linear systems. So we studied this Fuchsian system having 4 regular singular points at 0, t, 1, and infinity. So to this system, we can assign a quadruple of monodromy matrices, or rather a conjugacy class of quadruple of monodromy matrices. So going from here to here, well, of course, this is a rather transcendental map called Riemann-Hilbert map. And yes, John?
Just a trivial point about notation. Oleg, why do you write your connection matrix on the right instead of the left?
Yeah, I will show you later. It's for some technical reasons. Basically, it's to avoid some operators later on to act on the left instead of to the right. At least I found it even more confusing than this notation here. So I'm well aware that the standard choice is to put the fundamental matrix on the right, but well, hopefully I will convince you that for my purposes it is convenient.
Another trivial, maybe small remark that historically RH it is inverse map.
Yeah, again, we can talk about direct and inverse. Yeah.
So I would rather than put double arrow. If you talk about the Riemann-Hilbert correspondence, then you can write it double arrows. Yeah. But inverse map, it is historically, it is Riemann-Hilbert kind of map.
And actually, we are interested precisely in the inverse map. So given a conjugacy class of monodromy, we want to restore this equation here. So basically, given these 4 matrices, which satisfy this cyclic condition here, we and also whose eigenvalues are fixed in this way. So we want to restore from these M's the corresponding linear system. Right. And let me stress perhaps once again, I have said it already the last time, but I think it is like important point to understand is that we don't want to solve for phi. We don't want to find the fundamental matrix phi. We really want to find the differential equation for phi, which is a simpler problem. So this is an example of answers to this question in the 3-point case. So we have the 3-point Fuchsian system, singular points at 0, 1, and infinity. So now you see, if you want to find a case, so differential equations from M case, from monodromy, then the formulas for the coefficients are like really simple. So it's just basic, very basic linear algebra. How to find this conjugacy class of A's from their eigenvalues. But on the other hand, if you want to solve for phi, then you get, well, basically this expression here, so hypergeometric functions and so on. And so, of course, if you have managed to solve for phi, then you just use this linear system. You do, you compute phi minus 1 dz phi, and you get your A0 and A1. But clearly, I mean, to solving one using the solution of the point 2, it's like an overkill. Okay, and we will try to avoid passing by this second step to answer the first question. Okay, even though I mean this is the whole point of Riemann-Hilbert approach to Painlevé functions so far. So people usually solve approximately the problem for phi and then extract from the solution the asymptotics of matrices AK. And this is what we are not going to do. Okay, so I have also said that the construction of the inverse of this Riemann-Hilbert map is equivalent to solving Painlevé 6 equation. So Painlevé 6 equation, I write it in this matrix form. One can write a second order scalar equation if one wants, but the concrete form of this equation will depend on the function, on the invariant function on the space of these residues that you use in order to write your equation. So you can use, for example, this function here, or this function here, or even some more complicated combination. Now, it turns out that a very convenient choice is this one. Okay, so we take some particular combination of the traces of pair products of residues, and moreover, we declare that so this is going to be the logarithmic derivative of some function tau. Okay, so this is the famous Jimbo-Miller-Ueno tau function.
Oleg, I didn't understand what is that. Just a moment. Oh, is that the tau?
Yeah.
Oh, okay. Sorry, I didn't recognize it as tau.
So the point here is the following. So if somehow you have managed to reconstruct your linear system with given monodromy, then well, automatically your matrices A0, A1, AT will satisfy this system. But at no point I am going to solve any differential equation. So this will be obtained as a consequence of the reconstruction of the linear problem. Okay, so this was about The Fuchsian
Oleg,
case.
this, question notation, what you wrote as script, superscript theta subscript 4. You say a function on that. Is that the one-dimensional T parameter space?
Not quite. So this is, if you want, so this is where PQ of Painlevé will live in.
Ah,
this
that's
is
the whatever
two-dimensional phase space. Yeah.
I see.
Yes, and perhaps it is worth to mention another point. So we have fixed these parameters theta, the eigenvalues of monodromy. So this will be 4 parameters in Painlevé 6, and the remaining 2 monodromy parameters they will be the integrals of motion for our nonlinear differential equation. Okay, now, so I discussed so far only Fuchsian case because I didn't want to really go into the details about Stokes phenomenon. But actually the very same philosophy is valid for all confluent limits of Painlevé 6. So you have this nice picture from Chekhov, Rubtsov, and Mazoko, which kind of explains nicely what is going on. So if you start from a Fuchsian system having 4 regular singular points, then so this inverse Riemann, the construction of inverse Riemann-Hilbert map is equivalent to solving Painlevé 6. Now, if you collide 2 poles, so that instead of these 2 poles, 2 simple poles, you get a double pole here. So this is double pole. Then
could I just inquire about the notation? So I guess that's supposed to indicate some kind of cusp, isn't it? These sharp points.
Yes. I like to think about these cusps in terms of the Riemann-Hilbert problem associated to the Painlevé equation or the associated linear system. Another way to understand these cusps is that you take the quadratic differential, something like determinant of A of Z dz squared, and then you look at the degree of the pole of this differential plus minus 2, sorry. So this will be the number of cusps. Okay.
I think I understand the diagrams for 5 and 4. I cannot say that I understand 3' and 2' as well. There's 1 cusp and 2 holes.
Okay, so let me continue with the confluence diagram. So here we have double pole, right? 1 double pole and 2 simple poles. Here we have a triple pole and a simple one. And now when the number of poles becomes odd, one has to say a bit more. So this corresponds to a second order pole. So if we place it at 0, this will be a second order pole. However, the corresponding residue, so let's call it A minus 2. So this matrix is non-diagonalizable. Okay, so here not residue, the highest polar contribution. Here it is semi-simple, and here it is non-diagonalizable.
Is it nilpotent?
Yeah. Yes, because everything is traceless already. Good. So likewise, so here for Painlevé 3, generic Painlevé 3, we have two double poles. And this is a different Lux pair for the same generic Painlevé 3, where you have two simple poles and one second order pole, but with non-diagonalizable highest order contribution. And yeah, so perhaps the last example is this most degenerate Painlevé 3 equation. So this is because it will be relevant for us later on when we will try to connect these accessory parameter functions to Painlevé functions. So as you see, we have here two second order poles. So we place them at 0 and infinity. And now the highest order contribution at these poles should be non-diagonalizable. And this is what you see in this linear system, which is written here. So it corresponds precisely to this linear problem. So A naught is proportional to sigma minus 0, 1, 0, 0, and A2, which is the highest order contribution at infinity, well, is sigma plus. Okay, but anyhow, the point I want to make is that solving the inverse monodromy problem for the corresponding linear system is equivalent to solving the corresponding Painlevé equation. And the same confluence diagram, as it will turn out later, describes the linear differential equations of mature type. So Painlevé 6 is naturally associated to point equation. This most degenerate Painlevé 3 is associated to mature equation, and there is a whole bunch of other Schrödinger equations in between. Okay, so now,
Oleg, do you mean that there is just a one-to-one correspondence between this diagram and the Schrödinger-like equation diagram?
Yes. Mm-hmm.
And how this Schrödinger-like equation diagram relates to the hypergeometric subplane of this? You know, when you start with Gauss 3-point on sphere and goes to Weber, Whittaker, and
so this would be
Kummer degeneration. I mean,
yeah. So this would be F21.
yes.
Then this would be F11, confluent hypergeometric function.
Yeah.
Then from this you can go down to something like this, a quadrangle. So this is, I don't know which function to use, maybe d nu. So this is parabolic cylinder.
Yeah.
Or And so what can we do? What else can we do? Yeah,
We can also remove Casper
We
from
can also
F11.
Yeah.
one
Yeah.
cast from F11.
Mhm.
Yeah, so then this gives F01, which is Bessel.
Yes, this is the most. Yes.
Okay, and from here and from here,
We
we
get
can
triangle.
get,
You can Airy.
yeah, so this is A. Indeed. And actually,
as long as we're connecting these diagrams, I mean, somehow Painlevé 6 or the others at the boundary of the Weil chambers somehow reduce. So you recover, as many of you know, you recover hypergeometric as special solutions to Painlevé 6. Is there any way diagrammatically to see that?
yes.
But
yeah.
John, that is also the fact that you know, the special function solutions of at least for Painlevé 6, you can always associate them with one of the monodromy matrices to be the identity. So there is always an Okamoto transformation that will map your Riccati type solutions of Painlevé 6 to a solution of Painlevé 6 in which one of the monodromy matrices is the identity. So that's for me the intuitive way why we go from a sphere with 4 holes to a sphere with 3 holes, because it's like the 4th hole is not there because the monodromy is identity.
So we just erase one of the holes.
Yes, yes, exactly. Mm-hmm.
Okay.
So somehow the special solutions of Painlevé 6, they correspond to the situation where, so how should I draw it? When in this diagram, so somehow the right part or the left part trivializes. You have trivial monodromy, but well, actually, to make the statement more precise, I really need to go on.
Oleg, I'm not sure that in your right-hand side diagram you can go directly from this parabolic cylinder to Airy. It means that you are able to eliminate one cusp on this disk, and it is impossible. What is possible to go from Bessel? This is possible, but I'm not sure that the lowering arrow is possible.
This one.
Yes. This is
Vladimir, in a very simple way to say the same what you're probably saying is that area function is, of course, is expressible in terms of the basic function.
Area can be okay.
It is very simple formula, very at a particular case of basic function, but not parabolic cylinder function.
Yes, but so the fact that area is a special case of Bessel, it's not really this arrow.
I understand. But still,
so there is an equality between these two for special Bessel parameters. But there is also an asymptotic result where, well, you have to tend Bessel parameter to infinity and the argument in a fine-tuned way so that to obtain area. Well, I am pretty sure that this arrow also exists, but I never did that calculation myself. So, well, let me perhaps then leave this interrogation point here, but I don't think there is any problem in going from here to here.
It corresponds to nu going to infinity or something like that.
Yeah. Mm-hmm.
Yes, of course, if we consider this as a double scaling limit, that's they both work. Of course, I can go get area from parabolic cylinder functions.
Yeah, so you have something like d lambda, and the argument should scale with lambda in some way. So I don't know what to put here. But
Actually, maybe just a very short remark, because it might be that in this case where we're going from parabolic cylinder to area, we just not get just one area function, but two, because that's we know how it corresponds to
Yes.
ideology.
Because we actually, when we remove one cusp, what we do?
Yes,
we
so
are
we get
removing one
two
triangle.
yes. In this,
One cusp on the same border, Marta.
okay, now perhaps I have understood the confusion. So I'm not stating that from a single d nu you get a single area. So this is really a map of equations or the spaces of solutions of the corresponding linear differential equation. So it might be that one d nu transforms into a linear combination of areas. Yeah.
But these arrows should be kind of the limits of the connection, but not the solution, I guess, or not.
Can you repeat, please?
So you just said that you may have different area functions. So it means that you are just interested in the limits of the equation or the connection, but you don't care too much about the limit of the solutions. Am I right?
Actually, I do care.
Okay.
Yes, and it is actually a very interesting question, which I didn't want to discuss in the lectures. But so for example, already at this arrow, on which Marta has done some work. So how we know, of course, how to obtain Painlevé 5 as a formal scaling limit of Painlevé 6. But the question is, which solution of Painlevé 6 is mapped to which solution of Painlevé 5, right? So which we want to promote basically this formal confluence limit to a map between the corresponding spaces of solutions or of monodromy data, if you want.
But this is, of course, the main question, what we are doing when we do critical asymptotics in random matrices, for instance. Is exactly the issue, to map the monodromy data from one to another.
So I didn't plan to discuss this thing. Well,
sorry,
today,
I just...
but let me note, nevertheless, that the things that we are going to develop today, they allow to give a complete answer to this question for the upper part of this confluence diagram. For the lower part, it is well, more difficult. But here you have absolutely no problem. Volodya, you had a question?
No. I'm sorry that I interrupt you.
John, you still you have your hands up. You want to ask something? Okay.
Okay, so let's move on then. So now what will be our strategy of construction of this inverse Riemann-Hilbert map? Well, at the first step, we will convert the Fuchsian system we had into a Riemann-Hilbert problem on a circle, which will be characterized by a certain jump matrix J. So just to remind, what is a Riemann-Hilbert problem? So when we have some oriented contour, let's say in the complex plane or on the Riemann sphere, so we have some contour with direction. So the direction means that we have a plus side and a minus sign. So we are asking to find piecewise holomorphic functions psi plus and psi minus, which are related by this equation where J is some matrix defined on our contour. It's a map from gamma to, let's say, SL to C in our case. Okay. And so, yeah. And then once I have an impression that I hear myself 2 times.
It's probably best if everyone mutes themselves that they're not talking.
Right. So once we will convert our Fuchsian system into a Riemann-Hilbert problem set on a circle and characterized by a certain jump matrix J, we will forget about the isomonodromic origin of our problem, and we will assign to every such Riemann-Hilbert problem a tau function. So to any choice of this jump matrix, we will assign a certain number depending on J. And then we will show how this tau of J relates to the tau function of Jimbo, Miller, and UN. So now let me explain these steps one by one.
Oleg, just before you do it, I'm very interested in what you're about to say. We've been studying your paper with Kafaso and so on, and Gavrilenko, so on. What I'm troubled with, but I understand what you're doing, is you call it a tau function when it is not a function of t, it's a function of j. And that's not a tau function. I mean, it's something which, when you compose it with something, it becomes a tau function. But the tau function is a function of deformation parameter.
Well, call it tau constant, if you want. But if
until you put in dynamics,
yeah,
I don't see the tau function.
So actually, our jumps will appear in as members of a smooth family, depending on some parameter. So this parameter in the isomonodromic setting will be this t, the position of the fourth regular singular point. But actually, it is not even necessary. You could consider here, instead of t, you could put, I don't know, some monodromy exponent here.
But
so
am I right in saying that when you write down this Riemann-Hilbert problem, the dependence on the deformation is a priori in the psi minus or the psi plus, or possibly both, I don't know. So it's not as a function of j, but as a function of t, where the t dependence has been put in by hand in psi minus. Isn't that right?
No, not Joe. T and G, dependence of T and
J. Just forget about this Fuchsian system and isomonodromy. Simply suppose that the jump matrix that you have on the circle, it is of course a function of, so if we are in the complex plane of Z, so first of all, it will be a function of Z, right? With so some Laurent expansion here. But now we say that suppose that this jump matrix also depends on some parameter, any parameter. So in our problem, it can be the position of forced singularity. It can be monodromy exponent. Perhaps it can be something else.
But is it true? Just correct me if I'm wrong. I'm thinking of your recent paper with Capasso and Pavlo, that that in a sense it's working the other way around. You're giving the psi minus psi plus and saying, well, this is how we define J.
In the isomonodromic setting, this is the relevant construction of J.
Okay. Maybe it's the other half.
You could
I'm
ask,
jumping the gun.
but you could write this definition independently on how J is defined.
Well, okay. I don't want to divert from your talk, but there's two halves in your paper. One is isomonodromic and the other is Gelfand-Dickey. And I guess that Mattia was mainly responsible for that part. And there it looks definitely that he just defines some kind of linear exponential dependence on T in psi minus. And psi plus doesn't depend on T, it depends on the initial conditions. That's the point in your Grassmannian. So you just sort of work, I mean, it looks like reverse engineering that you decide that J is given by this equation, but in fact, you've already defined what psi minus, in that part, in the Gelfand-Dickey part, you've defined psi minus and you've defined psi plus.
Joe, I'm very sorry for interrupting, but many of our participants, they did not see that paper which you are discussing now with Oleg. So maybe we will just go on, because in his talks, well, what he is presenting now, it is self-sufficient. So you just want to discuss something which is not presented.
Okay, I pass.
Well, we can discuss after. Okay, so remember, we want to construct the reconstruct the linear system from its monodromy, and at the beginning we will pretend that we actually want to construct, want to solve for phi. Okay, and the initial Riemann-Hilbert problem, which this function phi of z satisfies, is, deceptively simple. So it's set on just a line. So we have, so this fundamental matrix has branch points at 0, t, 1, and infinity. So we can just connect these points by branch cuts, and the corresponding jumps will encode the monodromy. Okay. But we also have to remember that phi of z has a certain singular behavior is required to modify the problem that we have here. So to this end, remember that the solution of our Riemann-Hilbert problem, for example, in this region here, outside of all of the circles, is just phi of z, okay, the solution of the Fuchsian system. But now let us do the following thing. So we will first, I will erase the jump here and introduce an annulus bounded by two circles. Okay, so inside the annulus, the solution of my Riemann-Hilbert problem is going to be minus z to minus, well, let's call it sigma and minus sigma, some diagonal matrix, times phi of z, where this matrix here is nothing but the monodromy around a pair of points. Okay. Yes, and I will restore portions of the segment that we had before. Okay. So from now on, we will look more or less exclusively at what is going on in this annulus. Because I have multiplied the fundamental matrix by something which has exactly the opposite monodromy around this contour, it means that what we have here, well, it's a periodic function. It's it can be expanded into a Laurent series, and moreover, we can now do a little bit more. We can associate to our new Riemann-Hilbert problem two auxiliary Riemann-Hilbert problems, one of which is okay, how can I do it? So I will probably go down and make a mini version of this. So one auxiliary Riemann-Hilbert problem is this interior one, and another auxiliary Riemann-Hilbert problem is this one, the one which is associated to exterior contour. Now,
you could understand the exterior as having two holes, right? There's also infinity.
Yes, so actually this circle corresponds to 0. This for the exterior contour. This circle corresponds to infinity, and this corresponds to 1. And for the interior auxiliary Riemann-Hilbert problem, this one corresponds to 0, this one corresponds to t, and this one corresponds to infinity. So now, of course, this problem here is strictly equivalent to the Riemann-Hilbert problem we started with. So, I mean, suppose that we have found, let me put again here some colors. So suppose that we have found the solution of this Riemann-Hilbert problem inside the annulus. Then you just multiply it by minus z to this matrix sigma, and this gives you the, let me put here annulus. So this gives you the solution of the Fuchsian system. But now I will try to make use of this picture in order to simplify the contour of this Riemann-Hilbert problem. Namely, given this psi annulus, I will now introduce the following function. So, and I introduce psi bar of z, which is equal to psi annulus times psi minus of z. So it will be inside the annulus, and psi plus of z times psi annulus of, sorry, I forgot -1 here and here, psi annulus of z outside the annulus. Now I have to explain what are these psi minus and psi plus. So psi plus is the solution of auxiliary external Riemann-Hilbert problem. So why do I call it psi plus? Because, well, the solution of the exterior problem inside the annulus it will have only positive modes in the Laurent expansion. Okay, so it analytically continues until 0. And likewise, psi minus will be the solution of the interior Riemann auxiliary Riemann-Hilbert problem, which continues analytically up to infinity. Okay.
So, Oleg, are psi minus and psi minus expressible explicitly in terms of hypergeometric functions?
Yes, yes. So this is what I have shown you before here. So, so what is written here is basically psi minus. You see, you take out this singular coefficient, so you have to forget about this. And what remains is basically psi minus. And for psi plus, you have a similar formula. But what I am saying is actually applicable for Fuchsian systems in any rank, but starting from rank 3, unfortunately, we cannot express these auxiliary solutions in terms of hypergeometric functions. So I would say that so this psi plus and psi minus, they are useful building blocks, which, well, in rank 2, we can do something more about them.
So you can do this for the Garnier system?
Yes, except that for the Garnier system, we will have n minus 3 auxiliary 3-point Fuchsian system to introduce. So perhaps some of them, some of you have already understood that what is pictured here is actually a decomposition of this 4 punctured sphere into 2 pairs of pans. Now, if you want to have Garnier, so you will have, let's say, 5 points, the simplest non-trivial Garnier system. So now, instead of having just 1 annulus like this, we will have 2 of them. And so there will be 3 auxiliary solutions to introduce. Okay. Okay, let me come back to this picture, and let us look at this function psi bar. So when we have divided psi annulus by psi minus minus 1, it means that we have actually canceled all of the jumps inside this annulus. Okay, so this psi bar has no jumps here inside. Now, when we divide by psi plus, we cancel all of the jumps outside. Okay, so actually, sorry, I forgot to put here some circle. Let me put some circle. Circle C. So this is inside C and this is outside C. Okay. So we have canceled all jumps inside C and outside C. But since we have divided by different factors here and here, the price to pay is that we get a jump of psi bar on the circle C. Okay, and more precisely, what we have is that psi bar plus, or psi bar plus, corresponds to the values of psi bar on this part, on this side of the of the circle. So it means that it corresponds to this function here. So it is the same as psi bar minus, which is this function here, but multiplied by psi plus to compensate this, and multiplied by psi minus to -1 to get that. Okay. And so now look at what we get. So we have a Riemann-Hilbert problem for the function psi bar, which is strictly equivalent to our initial Fuchsian system. The jump in this Riemann-Hilbert problem is given by this expression. So this is the jump matrix. And at least in rank 2, this jump matrix is given by some hypergeometric functions, completely explicit. Okay.
Oleg, this was what I'm sorry, Sasha, but this was the remark that I was making before, that in a sense, psi minus and psi plus are known entities. They're given in terms of these hypergeometric, and J is just defined to equal psi inverse minus psi plus.
Excuse me, John, the choice you make for psi minus and psi plus is dictated by the problem you're solving. So in a sense, you know, it's not you fix psi minus and psi plus in such a way that they give you the right J.
No, I believe that Oleg wanted to kind of present, you know, first some sort of general concept where it has nothing to do with, you know, representing J of some in a different way by some auxiliary psis. And these general concepts are actually very close, John, to just Siegel-Wilson. So you have how you define tau function for Siegel-Wilsons. You have action of loop group. So the J is just the loop group action on your subspaces. And so tau function also depends on J. And J in terms is kind of Lorentz series when you have all infinitely many times.
Okay, just to make a remark about what Sasha said, yes, in this work, which Oleg is describing, they're putting on a very similar footing the isomonodromic problem, and well, not really Siegel-Wilson, but the Gelfand-Dickey, which is a kind of reduction. But in both cases, what happens is that, well, in the Siegel-Wilson or Gelfand-Dickey, psi minus is just given by hand. It's given as a linear exponential function, a matrix function. And psi plus is also given by hand. It's given by applying some group element to determine an element of the Grassmannian. So all the time dependence is in the first factor, and all of the Grassmannian group, Grassmannian element is in the second factor. And then you define J to be the product. In the isomonodromic case, I agree that there's some calculation that has gone, and it's really a Riemann-Hilbert type of calculation, but it is not this Riemann-Hilbert problem. It's the reduced one, the one with only two circles that has been solved by hypergeometric, and same thing for psi plus. And then the two are again stuck together, and then we call that J. Am I right, Oleg, in saying this?
Okay, let us just, you know, it is everything what Oleg is saying is self-consistent. Let's call tau functions. He is discussing the, you know, Gavrilenko, Lisovyy, Kafasa, Gavrilenko, Lisovyy tau function.
Let's call it rhythm
CJL tau function. Okay, so that is it is absolutely rigorously defined. So what? And there is of course connections with the Siegel-Wilson. That's it.
I wouldn't.
Yes,
let's talk about this afterwards.
Concrete example. An important thing, of course, in this example, this is what Oleg is going to say, is that he is able to write determinant representation of this tau function, which is much more efficient than determinant representation of Siegel-Wilson, say.
I don't agree with that second statement.
Okay. It is.
But, Well, let's put aside Segal-Wilson maybe. So what we are trying to do is the following. So suppose we have some arbitrary jump matrix on the circle. Now, the proposal is to introduce the following quantity, which is a determinant. Well, I have to explain the notations here. So the space H here is the space of square integrable functions on our circle. So this is, of course, it admits a decomposition into functions with only non-negative and negative modes. So P plus is the projection on H plus, this Segal projection. And so the tau function associated to this arbitrary jump matrix, or tau constant if you want. So this tau of J is defined as a Fredholm determinant of this operator on H plus. Okay. So far we are not talking about any factorization of the jump matrix. So you see, in the isomonodromic case, the jump matrix has this explicit factorization, and we want to solve for another factorization, which is psi plus bar psi minus bar minus 1. Okay. But so to define this object, we do not need to talk about psi plus minus or about psi bar plus minus. Okay. And it's precisely the point, because from now on, I forget about the, so I no longer pretend that I want to solve for psi bar. I just introduce this quantity, and I will try to show that this quantity in the isomonodromic case coincides up to a simple correction with the tau function of Jimbo-Miwa and Ueno.
Well, could I just interject one question here, because I'm fascinated with this connection between the two, but I only see the connection in your what you call the Widom constant formula. In the Gelfandicki case, it's clear what the Grassmannian is, and it is definitely not a general point in the Grassmannian. It's a very, very small subvariety of the Grassmannian, which is selected. But I'd like to ask you, in the isomonodromic case, do you have a point in either a Sato, Siegel-Wilson, whatever, Grassmannian associated with the solution?
I'm not sure we have.
You see,
no. Actually, I'm not ready to answer to this question. I guess whether.
Maybe we could leave this to the discussion after.
So in the isomonodromic case, you see there is a, we know what does it mean to describe all solutions. And so this construction, it covers all solutions, more or less. At least for generic monodromy, it covers all solutions. So there is nothing left outside. Okay, but I see that it's already time to go to conclusions. So we have introduced this object, tau of J, which has appeared long ago, even before the work of Jimbo-Miwa and Ueno. It was this work of Widom on the asymptotics of Bloch-Toeplitz determinants. And the next steps that we are going to make are the following. So we will discuss this variational formula for Widdom's determinant, which expresses the derivatives of tau of j in terms of solutions of this two factorization problems that I had. So I had j equal to psi minus -1 psi plus. So these in the isomonodromic case are known. And we had another problem, psi plus bar, psi minus bar. So this is equivalent to finding phi. Okay. So we are going to use this variational formula in order to well, differentiate the determinant and show that it coincides with this object here. So by differentiating and computing some residues, we will be able to recover this left side of Jimbo, Miva, and UN. But well, this will be perhaps the next time, right? Unless you want to that I continue now.
No, I think yes. Maybe it will be next time, right? I think everyone agree, because we'll have next time. Or Oleg, maybe you wanted to present more results. So what will be next time, actually?
Yes. So so first of all, I will try to explain a little bit how to actually compute this tau of j written in this form. So we will obtain at least the structure of the asymptotic expansion of tau of j in powers of t, in powers of isomonodromic time. And this will make the connection between Painlevé tau functions and C equal to 1 conformal blocks. And then I will try to explain what is the relation between Painlevé tau functions and accessory parameters from the first lecture.
Okay. So if so, let's thank Oleg.
Yeah, thank you, Oleg. I'm sorry, I have after 7 minutes, I have my class. So see you next time. Thank you very much.
Oleg, is it possible to continue talking, or do we have to end it?
Yes. So,
yeah,
so I think that there were questions on the way. So formally we'll conclude this session, but we'll continue with discussion, right? So let's thank Oleg again. And we just smoothly fall into discussion.
Okay, I'll have to go because I also have to record the class for next week. So.
Okay. See you, Martin.
Bye, Martin.
Thank you.
Okay, let's see who remains. Fabrizio, are you still here?